Mm.
Okay, good morning, everyone. This is Shixin. I'm a third-year PhD student from Brown University, supervised by Professor Pei Zhou. Today, I'm going to share our work advancing environmental sustainability in data centers while carbon depreciation models. So, to get started, I'm trying to considering buying a car. So I have calculated a lot about this. So to own a car, we need a one-time investment, which is a large amount of money. And to own a car, we need much more. We need additional recurring costs. We need to the gasolines. We need to repair the car and paying the insurance. We also need to do the parking fees. So for the one-time investment, how can I do myself a favor and make my life easier? The answer is probably getting a second-hand car. So we can see this is the depreciation curve of a car's price over the years. If we buy a brand new car, the good news is that we will have the newest features. For example, we have a better speaker, but bad news is that we will have to pay a large amount of money, especially nowadays. And if we have a second-hand car, you can see, for example, here is a 4-year-old car. It's affordable as the price depreciates. However, it's old and it may lack some features. And you can see one interesting fact about this curve is that it is nonlinear. The most of the value depreciates in the first years. From the first 3 years, the car's value depreciates from the 100% to 43%. And for the last 6 years, it only depreciates about 20% of this value. Moreover, I'm also considering owning a car versus using a Uber. So how can I evaluate this is I can calculate a per-use cost. If I can use the car every day, of course, we will have the one-time investment and we will have to pay a lot on the recurring costs. However, we can amortize these costs on a large amount of usage. So the per-use usage could be much lower. Another case is that we can using a car once per month. In this case, we still need to pay this one-time investment, and we need to pay much less on the gasoline, but we can only average out them in a few numbers of rides. As a result, the number of the cost per ride will be much higher. In this case, probably we should go for a Uber. The same thing applies when we're operating a data center. Here we have a Dell R840 servers, and it has the carbon emission in the whole life cycle, from the raw material to manufacturing and sending it to the data center. We're operating it, we will need to pay for the electricity and cooling. And finally, after it finishes its duty, we will recycle or discard it. That is the end of the life. So in this case, the manufacturing, of course, it's a one-time cost. We call it embodied cost, CEM. And for the operation, we will have this recurring cost, which comes with us along its lifetime, that is COP. So the embodied carbon and operational carbon is our main focus in this work because they take more than 9,500% of the overall carbon cost. This carbon cost is a huge amount. According to the vendor report, it costs 15,000 kilograms carbon dioxide equivalent in its lifetime, which means the per year carbon cost is can much have to be absorbed by 18 acres of US forests. So how large is 18 acres of US forests? Here is a Google map of our hotel. You can see that it has only 0.9 acres. So that means one server as this large will need 20 times area of forests compared with this hotel to absorb the carbon emission. So this is actually a huge number. How can we reduce the carbon cost and what is our design choices for this? We can consider a data center with accelerators. So we know that there are newer and older GPUs. From 1970s, we have the Volta generation of V100. And 2020, we have the A10G, that is the Ampere generation. And more recently, we have the Ada or say Hopper generation, which is much better. So The design choices for a data center carbon avail provisioner, the first thing is that we can, of course, upgrade our existing servers to a newer generation. So just like the new cars, they will have the nice new features. They will have a new architecture, better performance, better energy efficiency, so that we can reduce the operational carbon. But to buy a new car means that this board must be produced right away so that we will have an immediate embodied carbon investment. Another choice is that we can extend the lifetime of the existing servers, which means that we can save the embodied carbon cost. However, as say the V100, it may have a similar power of A10G, but it only have less than 1/2 of the TOPS. That means that the carbon will have a lower energy efficiency and as a result, a higher operational carbon. So the question is, how can we quantify these design choices? Or how can we quantify this trade-off? Well, one way to do this is to quantify the design choices, just like the per ride cost for our second-hand car. We can also quantify the per task carbon for each server. So let's consider this scenario. In 2020, we want to consider replacing a V100 server with a new A10G server. Here, we choose ResNet 50 as the application. So on V100 server, we have a 600 kilogram carbon dioxide equivalent embodied carbon and have this power. And we have profiled the latency for 1 million inference. And we also have the same thing for the A10G server. So we also have other assumptions about the lifetime and the carbon intensity, which means that how much carbon we need to pay for generating 1 kilowatt per hour energy. So the baseline solution is that we can simply average out the runtime to its lifetime. We have the execution time and we have the carbon cost, which is basically the embodied carbon times runtime over lifetime. And the operational carbon can be just the time times power times carbon, that is energy, times carbon intensity, that is carbon. The bad thing is, the problem here is that if we calculate them out, we can see that for the V100 server, the embodied carbon is 0.03, but for the A10G, it is only 0.002. And also, the A10G has a smaller operational carbon than the V100. This means that the newer CPU is always better than the old one in both embodied and operational carbon. So the reusing hardware shows no gain here. That means, should we always buy the new device? And the second thing here is that another problem is how we can consider how many A10Gs should we provision for the same target throughput amount. Of course, we can have the regular case, we have the one server with 90% of utilization, or we have made a mistake. We buy 3 A10G servers so that each one only runs at 30% of utilization. And we still use the baseline solution. And interestingly, we get the same results. And if we inspect the formula here, we can say it have no items about the utilization of the servers. So this means our current solution can show no difference between the low and high utilization. Of course, we can say if we buy more servers, we need to pay embodied carbon and the operational carbon in the idle time. This part is not quantified, and we call it as the secondary carbon. So the summary is the problems of the short part of the baseline method. First, they always prefer new devices because they have similar embodied carbon and better operational carbon, so which are inconsistent with the reuse principle. And also, they do not aware of the server utilization, so that they cannot distinguish good and bad provision. How do we solve this is by exploring different linear depreciation models for the embodied carbon. And we also show that the baseline method is actually the linear depreciation models for the embodied carbon. And we also show the nonlinear depreciation carbon will encourage the use of the older hardware. Also, we explore the secondary carbon accounting that accounts the carbon in the idle time into the per task carbon. And we show that this can promote high server utilization. Moreover, we study under different depreciation and secondary carbon accounting strategies. Before we show our results, we need to discuss what is a depreciation model. A depreciation model is a mathematical rule that allocates the depreciable value of an asset over its useful lifetime. So we have an init value and a salvage value, which is before the end of its life. And we have the lifetime, which is divided by different periods. And we can see after each period, we have a book value, which means the remaining value of this device after a certain time. And here, of course, it's a linear depreciation model. We also have the DB depreciation model, DDB, and SYD model. Don't be afraid about these formulas. We will just show the key ideas of them. Of course, we can see here we have the linear model and the DB model. The first year here is the depreciation of the DB model. That also means the carbon cost we use in this year. And this one is for the DB model. This is for the first year. That more values are depreciated in the DB model and means that more embodied carbon costs are assigned to the first year. And we also consider the third to fourth year. We can see that the linear model depreciates for the same amount, but the DB model depreciates much less. That means the last years. So as a result, the key idea for the linear depreciation model is that it pushes more embodied carbon to the first years. So next, we discuss how we quantify the per task model before we go to the results. We begin with the server specifications, and we use a framework called SCARIF to estimate the overall carbon cost in its overall lifetime. And then we distributed them to each year. That is where the depreciation model chimes in. And then we can calculate the per task embodied carbon with the T task, that is task time, and utilization. So how do we calculate the T task and U is while the application specifics. We first send the applications to the NVIDIA Triton to profile the best configuration about the throughput and the task time, and also their power in activated and idle time. And with this, we can compute the server utilization with the targeted throughput. And then we can compute the pre-task embodied carbon. And we also have the grid specs that means represents the efficiency of the power grid. With them, we can compute the per task operational carbon, which accounts for the carbon in both active state and the idle state. So then we can discuss the implication of the different depreciation models. Still, we use 2020 and ResNet 50 examples, and we set the target throughput at 200 inference per second. But to begin with, here is the carbon per task for the linear model, and the V100 will be higher than the A10G. This is because the linear model, they have very similar embodied carbon, so that it will attach the importance to the operational carbon. As a result, it will prefer fast and newer devices, which is incompatible with the reusing principle. Then we go to the DB model. We can see that it highlights the importance of the embodied carbon. That is because for the new device, we have a large amount of embodied carbon assigned for the first year. And for the old V100 server, it enjoys very low embodied carbon in the later years. And other models, it will have a similar flavor, but they are less aggressive to offload the carbons to the earlier years. Then let's go to the secondary carbon recovery. Here we can see still we have a V100 server running on different utilizations, and with the linear model, without the secondary carbon recovery, they do not coverage overall carbon cost, and they are all the same. That means they do not know about the server utilization. And here is the with secondary carbon recovery. It covers the cost at the idle time. So we can see that there will be a huge jump when the utilization is low because we distribute the carbon to the, we distribute a larger amount of in idle carbon or say secondary carbon to a few tasks. And as the utilization goes on, the per task carbon drops, and which is finally goes to very close to the carbon without secondary carbon recovery. And let's then combining them two together. So here we show the per task carbon cost on 100 GPUs with different utilizations and edges. We can see that the reuse is encouraged. Moreover, keeping high utilization is promoted. And finally, over-provisioning is punished. Because if we want to do over-provisioning, that is to buy more devices than we need, first we will replace old devices with new ones. And we will also lowering down the total utilization. That means we go from this square to somewhere near the peak of this figure. So that means we will be punished by over provisioning. And we also conduct a sensitivity study to study how different applications and carbon intensities affect the design choices. And here we still use V100 server and year one A10G server. We have more results on the original paper, and you are more than welcome to check them out. Here we show the y-axis means the carbon of V100 over A10G. So the y-axis is larger than 1, means V100 is better. So we can first see that for the linear model, they are almost smaller than 1. That means A10G is better than most of the applications. And with a higher carbon intensity, the gain of the A10G is better because higher carbon intensity casts importance on the operational carbon. And for the nonlinear operation model, we have flipped the design choice in almost all applications. And of course, for the higher the CI, the smaller the gain for V100 because it casts importance on the operational carbon instead of the embodied carbon. And we can see that when we compare different depreciation models, the DDB and SYD models are less aggressive, so the gains are smaller. And when the carbon intensity is high for some models with new device, for some models where the new device will have a much better gain, will have a significant improvement. And when the CI is high, it may flip the design choice in the DenseNet and ResNet 101. Finally, let's consider the multi-server scenario. This is a case study for a cluster of 6 servers, and we choose a lifetime to 3 or 6 years. We use the notion of a replacement cycle, which means for a 3-year lifetime, we will replace the oldest 1/3 servers every year. That also means we have 2 year 1, 2 year 2, and 2 year 3 servers. Here we report the per task carbon cost. First, we can see that the newer GPUs, the A10Gs in peak, is continuously better. And this fails to quantify the sunk carbon of the new A10G model because we want to pay an immediate carbon cost, but it's not reflected in this trend. However, when it comes to the DB model, we do see this trend. If we consider the new DB model, the first year A10G will be much higher because we pay the sunk. And for the second and third years, they are much better. This is also true for the 6-year lifetime. We show the similar trend line. And we also consider the effect of the secondary carbon recovery. Here we consider 2 greedy scheduling algorithms on the accelerators. We preferring new servers or preferring old servers. And here we set different utilization scheme, which is 0.8 and 0.3 to represent the good provisioning and over provisioning respectively. And here, without secondary carbon recovery, we can see that they are basically unaware about any provisioning. They are all the same and unaware about different scheduling. They are just the same. With good provisioning, we can see that there are slightly difference in the carbon cost for the prefer old and prefer new scheduling strategy, which is not a big difference. But with over-provisioning, we can see there is a huge carbon cost increase in both prefer old and prefer new schedulings. And we can also see that the prefer old and prefer new, they have a large difference. That means the secondary carbon makes it clear between good and bad provisioning and good bad scheduling. That is all for our work. Thank you very much. Yeah, I think that is it. Wait, let me pause recording.